My name is Marco Castronuovo. I come from Italy. I work for the Italian Space Agency in the Deep Space Observation and Exploration Unit. Today I will talk about orbits and their properties, so orbital dynamics. So now another important effect is the atmospheric drag. This is the principle, the main non-gravitational force acting on most satellites in lower orbits. Drag acts opposite to the direction of velocity vector, so is in a sense braking the satellite and removing energy from the orbit. This reduction of energy causes the orbit to get lower and so faster. So this is a kind of paradox, the fact that an acceleration, or better a deceleration, is causing an increase in speed. Now the lower altitude increases the drag itself, since the atmospheric density is increasing at lower altitudes. And when the satellite reaches a very low altitudes, approximately 200 kilometers, it re-enters, so its lifetime is extremely short. Above 600 kilometers, the lifetime due to drag will exceed the typical operational lifetime that is in most cases around 10 years. However, drag can still be an important factor of orbit maintenance. What is important to keep in mind is drag is very difficult to predict, nearly impossible, and even with very powerful means of computing that we have today, it is the major source of the unpredictability of satellite positions in future times. And this also introduces a lot of uncertainty when a satellite will and where it will re-enter the atmosphere. You may have known about satellites who had been out of control and were re-entering the Earth, and it was not exactly known where they would fall on the Earth. So a belt of confidence was given, and this region was getting smaller as time passed and as the time of re-entering was approaching. So it is difficult to do long-time predictions, but a certain level of confidence can be reached when a few hours away separate from the actual re-entering. Two main reasons are at the basis for this difficulty in prediction. Drag can vary as much as an order of magnitude due to the altitude of the spacecraft, and this is due particularly to the fact that the surfaces that are exposed to the wind, to the atmosphere, vary depending on the orientation of specific surfaces, such, for example, the solar arrays. So the attitude of the spacecraft must be known time by time with maximum accuracy, and this is quite difficult, especially when the satellite is out of control. Then the atmospheric density varies as much as 2 orders of magnitude, depending on solar activity level. which varies itself from time to time, depending on solar cycles and so on. So all these factors cause great uncertainty in the drug definition, and so in prediction of the position of the satellite in the lower layers of the atmosphere. The acceleration due to drag can be expressed quite easily as a combination of values that are typical for a satellite. We have drag coefficient CD that is depending on the shape of the object. For let's say a satellite of spherical or quite spherical shape is around 2.2. Rho is the atmospheric density that, as I said, is varying with height. Then we have the cross-sectional area A, and m is the satellite mass, while v is the velocity relative to the atmosphere. So as you see, the atmospheric drag varies with the square of the velocity, is directly proportional to the area exposed to the wind, to the atmospheric flux, and is inversely proportional to the mass. So if we consider the quantity m over cd times a, this is called ballistic coefficient, and is typically in the range between 25 and 100 kilogram per square meter for satellites. Where we have higher values, we have what are called cannonballs. So satellites with a very high mass and very small area exposed, where this causes a very limited effect of drag. For example, this is for satellites that are supposed to measure accurately the gravitational field, where you don't want the drag to be a very large perturbation to disturb this measurement. On the other side, when you have a very low ballistic coefficient, you have what are called solar sails, or sails, where very small masses correspond to large areas exposed to the air. As I said, the atmospheric density decreases approximately with exponential law as altitude increases, and so it can be expressed with this simple equation here. We can see in this graph the evolution of an elliptical orbit due to drag. We can see in the left side of the graph we had a very low perigee and a very high apogee, so a very elliptical orbit. And what we see is that at the beginning there's no change in perigee. The perigee stays constant while the apogee starts decreasing until the orbit reaches an almost circular shape. At that point, both the apogee and perigee decay very rapidly. This is due to the fact that most of the effect of drag is exerted around perigee, where you have a higher density. And if you imagine this force can be concentrated, can be imagined concentrated exactly at the perigee as a force in the direction opposite to the velocity. This is as if we were operating a maneuver at the perigee, exerting a delta V, decelerating the satellite, and the effect of this is exactly to lower the apogee height. We can see now an animation of this drag effect, where the only force acting on the satellite, apart from gravitation of the central body, is exactly the drag. Of course, this animation has an exaggerated effect, so the area is very large and the mass is very small. You can see that the effect on the semi-major axis is a net decrease in semi-major axis. So the net effect is circularization of the orbit. This, of course, depending on the application, is one of the sources of maintenance of the orbit. For example, orbits that are devoted to Earth observation, and then where you have to provide a control of the track, that is, you want the satellite to observe certain regions at regular intervals of time. You have to exert a specific maintenance of the orbit due to drag that changes the shape of the orbit, and so the period of time and consequently the track of the satellite moves, drifts on the Earth. So, as I anticipated before, the drag effect is not unique to a given altitude. It depends on the solar activity, and you can see here what is the delta V required to maintain an orbit at a certain altitude. Of course, this delta V depends on the specific characteristics of the satellite. So what we said, the ballistic coefficient depends on the kind of solar cycle that is actually present at that time. So we have just a rough estimate for a specific computation. All the values have to be known, and as I said, especially the attitude of the satellite must be known at every time.